Welcome and hello. This is a video exercise in HEC HMS. And in this exercise, I'm going to be dealing with sediment transport, specifically building a simple hydrologic network and dealing with sediment transport for both a subbasin and a reach. All right, what I have on the screen here is absolutely nothing except a blank HMS application, version 4.12. Everything I'm doing should work in later versions as well. All right, let's go ahead and go with File, New. I'm going to start from the absolute beginning. That's how I like to do things on some of these exercises. If this is your first exercise with sediment transport, you're in a good place because this is the first exercise I've done with sediment transport, and it's why I'm starting from the beginning. Go ahead and give your project a name and then find a location for it by clicking on the folder icon and then click Select. I'm going to go with US Customary Units and Create. Okay, first thing is going to be to create a basin model. I'll call it Basin 1. Great name. And then I'll expand that. Click on the basin model so I see it here in the main map panel. Next, I need to start building out my hydrologic network. So I'll go ahead and start with the subbasin. I'll call it Subbasin 1. And then I'm going to move that right there. I'm going to click on Subbasin 1 and define some of the properties. The area is going to be 20 miles squared. And then for these methods, loss, transform, and base flow, I'm just going to keep them as they are, which are my defaults of initial and constant, Clark unit hydrograph, and linear reservoir. So next what I need to do is go into these tabs and define them. Now, I haven't added erosion yet, which I will do in a little bit. If I click on basin or sediment, I would click on change this sediment from no to a yes. But I want to get the basics, the very beginning hydrology of my network set up first. So back to the subbasin. For the loss method, for initial loss, we'll say 0.1. For the constant infiltration, I'll say 0.05. And I'll say it's 1% impervious. Okay, next tab over is the transform method. I'm using Clark unit hydrograph for a 20 square mile subbasin. I'm just going to add some numbers in there. And then for base flow, this is linear reservoir. Let's go with groundwater initial, I'll say is 0. The fraction will be 1 for 100%. The groundwater coefficient, I'll say is 20, and we'll just keep with one layer, one reservoir here. All right, pretty simple setup there. Something else I need to do before I can create a simulation run is create a MET model and a controlled specification. The control specification is a little bit quicker, so let's knock that out first. I'll go up to Components, Control Specification Manager, New. Control 1 is a fine name. There's only going to be one of them. And then I will go ahead and define that in the Components editor down here. So I need to type in the start and end date time using this particular format. So I'm going to just use the first 10 days of January 2020. And then for the time interval, I'll leave it at 15 minutes and then click Save. All right, so that's the control specification. Now the meteorologic model is next. So I'll go Components, Meteorologic Model Manager, New. I'll just assume the name MET1 is fine. I can name it whatever I want though here. And then click Create. Okay. And then expand that and click on MET1. So right now, by default, the only method is the precipitation method, and that is specified hydrograph. This is actually what I want. It's a very simple method so that the rainfall falls on the subbasin based on the specified hydrograph. What I need to do here is provide a time series data set. And actually, before that, for the MET model, I need to say to associate it with basin 1. So I'm going to click on the MET model here, and then basin, and then change this no to a yes, and then click Save. So I'll click on Specified Hydrograph. Now I'm ready to specify that precipitation time series data set, which is what we need to do next. So I'm going to go ahead and create it now. I'm going to go Components, Time Series Data Manager. The data type will be the top one here. The top option is precipitation gauges. That's good. New. And then the name, I'm going to just call this Subbasin 1. Okay, so I know what to assign it to. All right, let's close that. Now for time series data, I'm going to click on my Subbasin 1 precipitation gauge. And then I'm going to do manual entry. It's going to be in units of incremental inches. And I'm going to use a 1 hour time step. All right, so I'll click Save there. I'm going to expand this time window. Click on the time window. And now I want to change this date time to the same date time range that I use for the control specification. So it's just going to be the first 10 days of 2020, just right like that. and save. Now, if I click on the table tab, now it should range for the first 10 days of 2020 on a 1 hour time interval as we specified. All right, perfect. Now I need this data and I don't want to just key it in. So what I've done is I've built an Excel file that wrong tab. There we go. That has, I just wrote an equation to generate the precipitation for a 10-day time period at a 1 hour interval. It's right here. There's the equation. And then I've got a plot over here as well with some random numbers kind of helping me randomize things. So I don't really like this particular rainfall event. I want a little bit more rainfall in the first 5 days. And I've got a value here that tells me the total rainfall for that 10-day period, which is 4.9 inches. So let me go ahead and generate a few others just to see what I like. There's one right there. So that's 3 inches, 1.8 inches, not enough. 15, that's probably too much. That's also too much. 1.6, not enough. I'm looking for something between maybe like 5 and 10 inches. Not enough. Okay, that's a good amount right there, actually, 8.16. So I'm going to go ahead and grab this data, copy it onto my clipboard, back to HMS, and then just right click, paste, and then there is my data. Okay, so I'm going to go save and just click on the graph. So this chart right here should look similar to what I have in my Excel file right here. Now I need to specify this subbasin and link it to the meteorologic model. I know we haven't talked about sedimentation yet, or erosion, and we're getting there. But when you start the model from scratch, you just have to jump through these hoops and do these tasks. So that's been assigned. Let's go ahead and run the simulation. So I'll create a simulation run. I'll run it. Once we get that working, we'll add the sediment. All right, so compute simulation run manager, new. Run one is fine. Basin one, met one, control one. It's all we have. Okay. So here in the compute toolbar, I'm going to go ahead and run it. If you don't see this compute toolbar or any other toolbar, you can go up to view toolbars and then toggle it on right here. Like for instance, I don't need 2D toolbar. I can toggle that off. So that's no longer here. All right, let's go ahead and see if this runs. Looks like it ran. Again, no sediment, but I just want to make sure that we have some flows. All right, looks pretty good. We've got some losses. We got some excess precipitation, base flow, hydrograph, looking good. We're ready for some sediment. All right, like I said, we'll go to the basin icon here and then change this sediment value from no to a yes, and then I'll save it. Now I need to define the sediment for this subbasin. So I'm going to click on the subbasin, and now I have this erosion method down here at the bottom. Okay, so I'm going to click that and then decide which erosion method to use. I'm going to go with LA debris method EQ2-5. And then I can click on this erosion tab that appeared for me to define some of the details here. So the AT factor, I'll keep that at 1. Relief ratio, I'll say 12. I'm going to say user specified fire factor as it is there and started at 3, which means there hasn't been a fire in over 10 years. So that should result in less sediments. We'll test it though to see if it does or not. Flow rate threshold, 1 CFS is fine. And then the exponent I'll say is 0.75. And then as for a gradation curve, I don't have that defined and it's not required anyway, but it does add some value when we look at the results in the breakdown between the different grain sizes. So I'm going to go ahead and actually add that. To do so, you'll go up to Components, Pair Data Manager. Now for the type, we want to select the diameter percent function and then click New. I'm going to call this GSD1 for grain size distribution 1. I may add a few more here. All right, so let's go to the pair data manager, diameter percentage functions, grain size distribution 1. I'm going to do a manual entry. And in that other worksheet in Excel is where I was playing around with some distributions here. I actually like this last one that I had created, so I'm going to use this first. Okay, so close that. And then this is actually going to be in millimeters. And it's asking me how, there's no data yet, so this is kind of a trivial question. But I'm about to put the data in here just by right click paste. All right, so if I click the graph here, you see that distribution of sizes. Looks good, and then I'll save. Now I can go back to my subbasin, click on that erosion tab, and assign the gradation to my GSD1 paired data set. All right, I think I'm ready to run the simulation again. So I'll save that and then click on the run. That was quick. Now I'm going to click on the results tab and then expand that simulation. I'm going to click on the subbasin now, and if I scroll down, you see we have a folder at the very bottom for sediment. So it kind of contains all the sediment data, and it doesn't kind of get intermixed with the other data that we would normally see without running sediment. So if I expand that, what we have is sediment load, and then a breakdown of sediment load by the four main soil types. And then the same thing with sediment volume, followed by a breakdown, bulk flow, and sediment concentration. All right, let's go ahead and look at sediment load. So this is cool. This shows the tons, and remember we're on a 15-minute time interval according to our control specification. So this is similar to the flow rate, right? Let's actually combine this graph with the outflow from the subbasin so we can kind of see how the two relate. But there's obviously going to be some correlation here. So I'm just going to scroll up, hold down the control key, and then click on this outflow. All right. Yeah, obviously. And then I'm going to click on the graph button up here just to bring it up into view. Increase sedimentation at the same time as some outflow. I guess I'm a little surprised that this peak right here at the end of day 9 is about 2/3 the peak at day 4 of the main peak, with just a small little peak in the outflow. But that could be because a lot of reasons I don't want to speculate. But yeah, a lot of conclusions can be drawn just from this plot alone. One thing I'm curious about before we move on to building a reach in our network is what effect does that fire factor variable come into play? Because I mentioned we set it at 3, which means there hasn't been a fire in 10 plus years. But if I set it to, I believe, 6.5, that refers to a recent fire. So let's remember some of these numbers, like the peak sediment load here is 350, 340. Yeah, so let's go ahead and check that out. Before we do, let me go ahead and I want to look at the breakdown between the different soil types. So here is the clay, here's the silt, sand, and gravel. I can't really tell from the small preview plot, so I'm going to click on the graph up here, resize it a little bit. All right, I modified the properties, and we can see red and green are the two main contributors by mass. Green is the most, that's the silt. Red is the sand, so there's a small amount of gravel or clay involved. All right, good to know. That's mostly because of the grain size distribution. It's not because of the flow too much. I just don't think there's a ton of clay or gravel in the sediment. All right, next I want to go back to change that fire factor. So I'm going to go to the Components tab, click on the subbasin, and then in the Erosion tab here, I'm going to change this fire factor to a 6.5. Save. Now remember last time the maximum sediment got up to 340, and that's tons in a 15-minute time period. Now I saved it with that higher fire factor of 6.5. I'm going to run it again. Now the results should update. So let me click on sediment and then load now. And boom, we just quadrupled, almost 3+ times increased our value. It looks like it's more than 1,600, almost 5 times sediment load. So this shows how the exact same rainfall event, the rainfall event that I simulated at least, generates 3 or 4 times as much sediment just due to a recent fire event. That's pretty significant. All right. Well, we could play around with this forever. What I want to do now is add a reach element and a sink element, and then add some sediment routing method to the reach, and then run another simulation and check out what happens. All right, so go to the components editor, and then actually I can just go up here and click on reach, and then I'll draw a reach right there. I'll call it reach 1. That looks good. And just for some closure, I'll put a sink right there. And then I'm going to connect everything here. So click on the subbasin, right click, connect downstream, and then click on the reach. I'm going to do the same thing with the reach. I'm going to single left click to select, right click, and then connect downstream, and there's sink 1. All right, everything is connected. Now what I want to do for the reach is select the components editor here. I'm going to change this routing to a Muskingum-Kung. The options that you want to use, and I learned this the hard way, is you have to use a reach that has a cross section that's defined. So most of these do not require a required cross section shape, but Muskingum-Kung does, as well as kinematic wave. This first one, I believe. Hold on, let me check. Kinematic wave, yes. Here's the shape there, and then if I go back to Muskingum-Kung routing, here's the shape there. All right, so make sure you use one of those two reach routing methods. And then I'll go ahead and define the properties here and then go back and assign a sediment routing method and define those properties, and then we'll run it. All right, so we are using Muskingum-Kung. I'm just going to go ahead and throw in some numbers here. So I'll say it's 100,000 feet is the length of the reach, which is what, 18 miles? I don't know. Manning's N will be 0.03. I'll use auto. The index flow will be, I don't know, 100 CFS. We can come back and change this. I'm more interested in the sediment though. And then the shape, I'm going to go with the trapezoid. Yeah, that's fine. The bottom width, I'm just going to make up something kind of generic. And then an invert, I'll also kind of use something generic. All right, click Save. Now let's go back to the main Reach tab here in the Components Editor. Our sediment method, we have a number of choices. Let's go with Linear Reservoir, and then I'll click on the Sediment tab right here. Now for the retention of the 4 different main soil types, I need to type in some numbers here. Okay, I think those are the numbers from the user's manual, so I don't have a strong feel for what to use. But if you do have specific information about your sediment that you're using, like you would obviously update it here, and you would also update it in, if you click on the basin icon up here in the Watershed Explorer, click on this sediment tab. If you know like the specific unit weight or the specific gravity, or also this transport method, I need to set that to something. There's a whole lot more options to be specific with your sediment data that I'm just kind of skipping over for the sake of getting the model to work and giving us some results. All right, back to the reach and then the sediment tab. The initial gradient is required, so I'm going to use the same, the gradation, the same gradation that we used for our subbasin. And then the bed width. This got me, I'm going to go through the same steps that I went through before. I'm going to say 10 and 10. You'll see what happens, and then we'll change it back to something more realistic. And then a 2 right there. All right, I think we're ready to rock and roll with our next simulation. So I'm going to go ahead and run it. All right, that looks good. I can tell that the log data now is reporting some reach sediment information. That's fine. So let's go to the results tab. And then here is the subbasin. And then here is the sediment tab. So let's open that up. And then here is the load. Now we didn't change the subbasin, so we really shouldn't expect to see anything different here. Now let's scroll down to the reach, and then at the bottom here we have a sediment folder. I'll expand that, and I'll click on sediment load. Now what we see, yeah, this is what I was expecting to see. There's a huge spike right in the beginning, and you may wonder why, because everything else looks pretty much normal. It matches the same shape as the sedograph from the subbasin and from even the hydrograph for the most part. But this huge spike right here was that 10 feet by 10 feet of sediment just waiting in the reach to get flushed out on the first storm. At least that's what I think happened. So what I'm going to do is go back and change that bed width and depth parameters here. So components, reach, and then sediment. I'm going to just change it to something modest like 1 and 1. So we should still see a spike, but nothing as dramatic as we did with that previous simulation results. Okay, so that's done. Results, reach, sediment, and then sediment load. Oh, is that for the reach? Yeah, it's done. Okay, so there's really no initial spike like we saw before. As before, we can go ahead and look at the breakdown between the 4 different types of soil, which appear to be similar to what we had before. I'm not going to colorize it. It looks pretty much what it did before. Something else that may be curious is to see how some of the heavier soils, like the gravel and the sand, would experience more attenuation in the reach. And I could monitor that as well. So if I click on the sand here at the end of the reach, and then also hold down Control, click on the sand as it begins the reach, which is when it leaves the subbasin, which would be right here. I can see that lag and attenuation within the sand for this sedograph. So what we're looking at here may look like a hydrograph, but it's not. It's the sediment. I'm going to change the properties real quick. Okay, so to do that, you can just go ahead and I like to make the lines a little bit thicker, and then obviously different colors too helps distinguish the multiple lines from each other. I'll go with blue. You know what? I'm going to change the first one to red. So they're they contrast very well. All right, so blue is when the sedograph leaving the subbasin, and then red is the sedograph as it leaves the reach, the downstream end of the reach. So there's a attenuation within the sediment itself, pretty Pretty cool concept. If I did the same thing with the clay, let's go ahead and see what happens there. Now, there's not a ton of clay, but there is some. It should be enough to get a plot out of. That is what I highlighted for the subbasin, and then this is for the reach. Okay, yeah, that makes sense. There's very little attenuation because it travels so fast. Let me go ahead and open that up. All right, this is what the clay looks like. And I'm not going to do the other two soil types, but you get the idea. There's very little attenuation because the clay is basically water. It's transporting much faster than the sand is, and we already set that parameter when we went to the reach, the sediment. This 2.7 is much faster than the 7.2. Also, the sink should really have the same information as the reach itself, but let's just confirm that because it's here and we need to put it to use for something. It has its own sediment folder, so I'll click that. And then here is the load. Here's the breakdown for the individual soil types. All right. There's also volume as well, which is a similar component as the sediment. Of course, it has different units. And this last one here is combined bulk flow. All right. Well, that was it for this exercise. This is the first exercise on sediment transport. We built a subbasin and a reach and a sink. We connected it together. We ran it without sediment, and then we added sediment, and we ran the simulation and viewed the results.